In the previous video, we had discussed the basic introduction of what a buffer solution is and how it functions, like how minor changes in pH does not affect the pH of the solution itself. And that's like we had a basic understanding of how buffers work. Feel free to check it out. In this video, we are going to be talking about designing a buffer solution, and we will be ending it with a very important concept called Henderson-Hasselbalch Equation. So let's begin. So we're going to start off with the preparation of acidic buffers. So acidic buffers contain two things, right? One of them is a weak acid and the second one is its salt with a strong base. The value of pKa and pKb and equilibrium constants, all of these are very helpful for us to be able to design buffer solutions. So we are going to start off with acidic, and in the case of acidic buffer, we'll go through and understand all of the steps. But in case of basic buffers, we're just going to get the end results. Okay, so first of all, we're taking this equation. Ha plus H2O gives rise to H3O plus A minus, where Ha is a weak acid, right? So the value of Ka for this particular chemical equation, which is equal to H3O plus, concentration of H3O plus A minus divided by concentration of Ha. Now, Ka is basically the dissociation constant of the acid, of the weak acid. We're not considering the concentration of water because you have excess of water and the changes in pH does not affect the concentration of water. It takes a lot for the concentration of water to be affected. So we will always, as always, ignore the concentration of water. Now, and the the concentration of Ha, that is Ha is the weak acid. Okay. Now, and I've written this down and I'm just copy pasting it onto the presentation, which is why it's taking me a second. Now, when we rearrange this equation, so we switch this to this side and we brought this to the denominator, Ha to the numerator, and then we switch sides. So you get this particular equation, a concentration of H3O plus equals to Ka concentration of Ha by concentration of A minus. Now, after which we are going to be taking the logarithm on both sides. When you do that, what do you get is log H3O plus equals to log Ka plus log Ha by A minus concentrations. Okay. Now, when you take a negative, adding a negative symbol in front of all of them, so we're just taking the subtraction. We're multiplying it all with a minus, you get this particular equation. And if you remember, minus log H3O plus is nothing but pH, and minus log Ka equals to pKa. So that is exactly what we are going to do now. We're going to substitute, I am so sorry. Okay, wait, yes, we did it. So we're substituting minus log H3O plus with pH and minus log Ka equals to pKa. I'm actually going to separate these two because it's looking really bad. So pKa. Now when we substitute those values, you get this equation. So pH equals to pKa plus log A minus by Ha. The reason we switched it is because we got back the positive sign, and so we have the numerator as A minus divided by concentration of Ha. Okay, and this basically is the Henderson-Hasselbalch equation. Oh God. All right. So this is the Henderson-Hasselbalch equation. So pH equals to pKa plus log of conjugate base A minus by the conjugate acid Ha. Now, if you think about it, the concentration, so this A minus by Ha, right? Just give me a second. Okay. Again, learning. We're all learning here. So the write it here directly, and that is perfectly fine. Okay, so this That is the concentration of A minus divided by HA. This is equal to nothing but the ratio of concentration of the acid, concentration of the conjugate base of the acid divided by the acid in the mixture. Now, the value HA, now if you think about the HA, which is the concentration of the acid, it is a weak acid, right? So it does not ionize as much as, let's say, if we had a strong acid. So this there is a negligible difference when it is in the solution. So HA is almost equal to the concentration of the acid, because it is not dissociating as much as, a strong acid would. In the same way, the A minus, now we already established that HA, which is a weak acid, when it dissociates, it's not doing much of that. So it's not going to contribute a lot to the concentration of the A minus ions. So this A minus is going to be coming only from our salt, right? The salt with the strong base. I apologize for that. So the concentration of A minus is approximately going to be equal to the concentration of the salt. Okay, HA we're getting from the acid, the original concentration of the acid, because it does not want to dissociate as much. And in the case of A minus, we're getting it from the salt itself because, well, it's a salt and it likes to ionize, right? So from all of that, from all of these things, you will get this particular relationship. This particular relationship where you have pH equals to pKa. Oh my gosh. Okay, pH equals to pKa minus log or plus log salt concentration divided by the acid concentration, because you have the salt, which is giving us the A minus ions, and you have the acid, which is giving us the HA ions. Okay, so when the concentration of salt and acid, when both of these are equal to each other, then you will have pH equal to pKa. Right, when concentration of salt equals to concentration of acid, it will become log 1, which is equal to 0. That's when pH equals to pKa. So basically, what I'm trying to get to is when, let's take the example of acetic acid. Okay, acetic acid and its salt with sodium acetate. So the pKa value for acetic acid is 4.76. The pH of the buffer solution of these two mixed together is at 4.76. It's able to maintain the pH at 4.76. It's able to act as a buffer at 4.76. So that is how we're able to use this particular equation for us to calculate the value, or for us to be able to design a buffer. Essentially, the pKa equals to pH. So we are using the pKa value, and think about this. The concentration of the salt is equal to concentration of acid because it is going to be an equimolar buffer solution. That's what we've always spoken about when it's a buffer solution. And so because of that, we're using the value of pKa to figure out the concentration, or to figure out the pH, and that's how we're able to design a buffer solution. In case of bases, you have the same equation where it is going to be POH equals to pKb plus log conjugate acid, which is BH plus, by the base. Now in your textbooks, what they've done is they've used these two relationships, and they have we've actually tried to change, or not change, I won't say change, I'm sorry, I shouldn't have said change. But we've tried to use these relationships to be able to calculate the pH. Okay, so you have pH plus POH equals to pKw. And so you just substitute for POH, you're using pKw minus pH. And then pKa plus pKb equals to pKw. Right, so pKb will be equal to pKw minus pKa. When you substitute all of these things, you are supposed to get this particular relationship. where pKw minus pH, and then after which what they've done is they've ended it with you getting, so in your textbooks they've said that pH equals to pKa plus log BH by B. But I don't think that that might be right, because when you substitute all the values, you are left with pH equals to pKa plus log B by BH plus, because you have to switch the numerator and the denominator. If not, you'll be left with a negative log. Again, if anybody has any suggestions with respect to this, feel free to let me know. I'm not sure if this is actually right, but the important thing for us to remember is pOH equal to pKb plus log conjugate acid by base. And if you have the value of pKa of the base, when you have equimolar solutions, the concentration of B and BH plus is anyway going to be equal, because it's going to be an equimolar solution. And so you will get log 1, which is equal to 0. So that's when you're left with pH equal to pKa again. Now, when you have the example they've given in your textbooks is, if I'm not wrong, you've given ammonium. I cannot for the life of me remember. Okay, hang on. Yeah, so you have the buffer solution formed with ammonium chloride and ammonium hydroxide. Ammonium hydroxide is the weak base, and the pKa value for ammonia is 9.25. So yeah. 9.25, and so the buffer solution of ammonium hydroxide, equimolar concentration of ammonium hydroxide with ammonium chloride, will give us a pH of 9.25. So basically all of these things are very useful for us to be able to design a buffer solution. Okay, so all you need to remember is this particular equation, and you need to remember the relationship between the concentration of HA and A minus with acids and salt respectively. Yes. Now we're just going to look at Henderson-Hasselbalch. These were given, this particular equation is very important in biochemistry and chemistry. It was given to it was made by two scientists, Lawrence Joseph Henderson and Carl Albert Hasselbalch. And Lawrence Joseph Henderson was a biochemist, and he was the one who came up the equation in the first place. And what he did was he tried to calculate the hydrogen concentration in bicarbonate buffer solution. That's how he came up with the equation, but it did not have the logarithmic scale. It was in 1908 is when he came up with the equation, and in 1909, when Sorensen introduced the pH terminology, Hasselbalch was able to use the Henderson equation and add logarithm to it, and that's when it became the Henderson-Hasselbalch equation. So that's just a basic idea of the Henderson-Hasselbalch equation and how we create buffer solutions. With that, we're done with designing a buffer solution. Remember the fact that the value of pKa is very important for us to identify, for us to be able to design a buffer solution, and that's what's deciding that that's what's deciding the pH of our buffer. With that, we're done with this particular topic. In the next one, we're going to be talking about solubility equilibria of sparingly soluble salts.